All right, so based off of the last one we looked at, we want to figure out places where functions will fail to be differentiable. One of them we saw already was when you have like that piecewise function where we have a corner. Any place where we have a corner, the derivative or the slope is different on one side. Here it's positive, here it's abruptly negative. That will not have a derivative at that corner location. So corners do not have derivatives. Also, places like this are sometimes also on graphs called cusps, but they're basically the same thing, corners, cusps. You have a point on there that, because it's an abrupt point and it changes slopes very quickly, it does not have a derivative there. Obviously, any place where it's discontinuous will not have a derivative. So this one at A does not have a derivative because it's not continuous here. There's this jump in between, so you can't have a derivative anywhere the graph is not continuous. One last place you do not have derivatives, and this is not necessarily maybe a function because it doesn't pass our vertical line test, but there are graphs we're going to be looking at, such as circles and things called ellipses. These have places where derivative doesn't exist. Anywhere where it becomes vertical on your picture, if your graph would do that, it does not have a derivative because we know the slope of that is undefined. Slope of a vertical line is undefined, so it doesn't have a derivative then there. So same thing with circles and ellipses. Right here and right here, those points on the edges don't have a derivative because the slope is undefined. Same thing with this ellipse here and here, it would not have a derivative because the tangent line slope would be vertical, therefore not existing. This theorem is saying if f is differentiable at A, then it is continuous at A. That is a true statement. Anywhere that you have a derivative must mean it's continuous then. So it's kind of like what we were talking about here. If we know there's a derivative, it can't be discontinuous then because we can't have a derivative at that location. So we know if you do have a derivative, like this point right here would have a derivative, it's got to be continuous there. So that statement, anytime in a problem they tell you something is differentiable, you know it's going to be continuous as well. Is the converse of this statement true? If a function is continuous, then it is differentiable. Hopefully in your head you are thinking no. What is a counter example that would prove that the statement's not true? Corner, it would be an example, or vertical part to your graph are both counter examples here. Corner and vertical part, it's continuous, like we saw before, but not differentiable. So those would be two examples, like a corner. This graph is definitely continuous. I can trace the whole thing without picking up my pencil, but no derivative there. So that statement's not true. If something's continuous, doesn't necessarily make it differentiable. But if you are differentiable, automatically means you're going to be continuous. Let's look at one example here. Where does the graph of f of x equals x to the 2/3 not have a derivative? You can plug that in your calculator to see what the graph looks like here. Enter it as x and then do exponent 2/3. Hit graph, and you should get a graph that looks something like this here. Where does this one not have a derivative? All these points here, we can definitely find the slope. It's a gradual change. Same thing here. All these places do. The one spot where this one doesn't is at x equals 0 here. You got a corner or cusp there. That would be an example of a cusp, but corner, same thing. You're not going to have a derivative at that point. So at x equals 0, there's no derivative. Otherwise, all the other points on this graph do have a rate of change or slope at those other points.